Welcome to this episode of the Structural Engineering Channel, a podcast focused on helping structural engineering professionals stay up to date on technical trends in the field and to help them succeed in their careers and lives. In this episode, we'll be talking with Sean Brady, a forensic structural engineer who has dedicated his career to understanding complex systems. Sean will talk about the importance of considering these interactions in complex systems and how this knowledge can help prevent future failures. He'll also discuss the role of the peer review in the Miami bridge collapse of 2018 and explains why humans sometimes have difficulty understanding these complex systems. I'm your co-host, Matt Picardle, and this is the Structural Engineering Channel podcast. Now let's jump into our conversation of the week with Sean.
This episode of the Structural Engineering Channel is brought to you by PPI, a leader in engineering exam prep for the PE structural exam. PPI provides expert prep courses and study resources designed to help you pass the PE structural exam the first time. PPI's PE structural course is fully updated and taught with October 2021 code references and includes new editions of their PE structural books. PPI's live online courses include hours of lectures, problem-solving demonstrations, exam strategy sessions, office hours, and a passing guarantee. When you take a live online course, PPI guarantees you will pass, or you can take the on-demand course for free. PPI has helped engineers achieve their licensing goals since 1975. Check out PPI today at PPI2pass.com to see all of the resources available for PE structural exam prep. Again, that's PPI2pass.com. Sean,
thanks so much for joining us today. Could you tell us a little bit about your background as a forensic structural engineer and how it led to your current work in complexity science?
Yeah, so I'm a structural engineer, never really practiced as a designer, sort of came straight out of academia and went into looking at old structures and how they actually work, particularly bridges. So spent a lot of work doing actual real measurements on bridges and real modeling of bridges and looked at the gap between how we design things and how things actually work in real life. So I really enjoy that space. And when you play in that space, that naturally sort of brings you to forensics, because the key sort of speciality I have on the structural side is understanding the causes of failure, which is fundamentally all about what is the sequence of events or that led to this structural collapse or this structural disaster. And that really is all about knowing how structures behave in the real world as opposed to on paper, and where things go wrong on the day. So I really got into that forensic side of things probably about 13, 14 years ago, and decided that that's fundamentally where we were going to specialize. And we did a lot of expert witness work, because usually the lawyers get involved whenever there's some sort of engineering failure. And we, in those early days, were all about finding out the technical and just purely the technical cause of failure. But the more you investigate and the more you read about what causes other structural failures, there's excellent literature came out of the US and out of the UK on it over the last sort of 30 or 40 years. You find we keep repeating the same technical causes of failure. And this got me really interested in, well, why do we do that? You know, if we know why we technically knock things down, why do we seem unable to prevent repeating that? And what you find is, to answer those questions, you have to start looking at the human and organizational causes of failure. And what you discover is that the reason we knock things down in structural engineering is pretty much the same reason as why things go wrong in hospitals and operating theaters and why businesses fail. Failure fundamentally happens, I think, regardless of the profession you're in, because we are governed by organizations and we're governed by people, and we tend to set those things up in the same way, and we tend to let them behave in the same way. So it shouldn't be surprising to us that I think we fail things in the same way from an organizational perspective. And what that does is that brings you then to complexity science, and it's probably best explaining why it brings you to complexity science by way of having a chat about an example.
I was going to bring up, I know one thing I wanted to talk about was the I don't know if this was relevant, the Miami bridge collapse in 2018 is Was that something that you wanted to talk about as well?
Yeah, the Miami Bridge collapse is a really interesting failure to talk about, and it's a really good introduction if you're not familiar with complexity science, where complexity science and structural engineering sort of come together. So the Miami Bridge was under construction in Miami, Florida in 2018. It was a reinforced and pre-stressed concrete structure. It was a simply supported span. It was designed and built off-site, and then it was moved out over the roadway in March 2018. Now, the key thing about this bridge, or it could have been February 2018, but the key thing about this bridge was that almost from the very beginning, when they made it carry its own load, when they removed the formwork, the bridge started to crack. And over the 3 weeks it took to move this bridge out over the highway, these cracks grew and grew and grew and became pretty horrific until one day they were applying some pre-stress or post-tensioning to the bridge. They overloaded one of the cracked joints. The joint failed explosively. The bridge collapsed. What turned this into a real tragedy was it collapsed over a road with moving traffic. The road was open, and we had 6 fatalities from the failure. Now, we could talk a lot about why the cracks seemed to be ignored and why they didn't get the attention they needed and why didn't they go back and review the design. But it's much more interesting to talk about the peer review process here, because what they discovered, the National Transportation Safety Board, was that there was some very significant design errors made in the bridge, particularly at one of the key joints. And the real question is, well, why did that happen? And why didn't the peer review, which should have been checking the joints and all the stages of construction of the bridge, not identify this error? And they didn't. And they didn't identify the error in the peer review because they never checked the connections to make sure they were okay. And they never checked all the different stages of design of the bridge. So it's really interesting to think of why that is. Why, when we're trying to prevent these things in the failure or in the future, what should we learn from this failure in terms of understanding why those things were missed? And that's where we come to complexity science.
And can you explain what complexity science is for those that aren't familiar, and why is it important in understanding these complex systems similar to the Miami Bridge collapse?
So fundamentally, complex systems or complexity science is about how we think about systems. And we humans, it turns out, are not very good at thinking about systems. And the way to think about this bridge is that it was a system that produced it. It was a system bringing together a designer, a contractor, a peer reviewer, a client. And what we're really interested in is, how does that system work? And complexity science is really good at helping us think about how these systems work. And we'll come to why that is in a second.
Sean, can you explain why you think humans have a hard time or understanding these complex systems?
Yeah, so it really comes down to how we've been trained to think about systems, not just engineers, but all of us. And we've typically been trained that if you want to understand a system, all you have to do is break that system down into its parts or its agents. And once we understand each of those parts or agents, we can put the system back together again and we'll understand what it'll do. In other words, we say that the system is the sum of its parts. What we see in complex systems is something quite different. We see that when we break these systems down and understand the agents, when we put them back together again, we get different behavior. We get what's called emergent behavior. The best example I like is an ant colony, right? So let's say you want to understand an ant colony and how it works, because it produces very sophisticated behavior. When you go at a Newtonian way or a reductionist way of thinking about that system, it would say, let's capture some ants and let's study each of the ants. The problem is, when you study an ant, ants are not particularly smart, and you're left with a gap between, well, how does this ant produce this sophisticated behavior when we put them all together? In other words, how do they produce a system that's much more than the sum of their parts? And that we find that really hard with how we think about systems, and how systems actually work, and we'll come to, I'll probably leave it there, and we'll come to how these systems actually work and how we should think about them. But fundamentally, it's this reductionist approach that causes the problem. We cannot understand these systems by simply breaking them down to their parts.
Yeah, so I know you also mentioned as a follow up to that it's not just here are the parts, you put it together, you get X. It's you have a bunch of parts, you put them together. I mean, and depending on maybe the different types of layers or whatnot and how they interact with each other, you might get something a little more different. I remember you mentioned something about non-linear. It's not just from here to here. It can go different places and uh, it can get complex. Yeah, let's jump more into that. I know you wanted to jump more into the ant colony, or I know one of your previous examples is starlings flocking. Maybe can you go into some of those examples?
Yeah, this is a wonderful example of complexity. So I presume, if you're listening, you'll have seen at least videos of starlings, the birds flocking, and you get these incredible waves of birds moving in a flock that seem to swirl and twist in the sky. And when you look at this, it looks really quite organized. It looks like people know, or their starlings know what's actually going on here. And this actually confused scientists for a long time. How does it work? How, is there a boss bird who's in charge? How did they do this really eloquent dance? Where's the conductor? Where's the music score that they do this to? And what they discovered was that these flocks of starlings don't work by top-down rules, the way we think of engineering structures, where we write down that one equation that describes how they work. Instead, they work from the bottom up. And you can build a starling model where you give starlings 3 local rules. So you basically say, if you're a starling, you are going to interact with your neighboring starlings in these ways. And these are things like turn towards where other starlings are, try and move closer to where the other starlings are. But if you're going to hit a starling, go off in the other direction. And what's extraordinary is when you run these, you can put that in a model called an agent-based model, and you run it, you get very realistic starling-like behavior. And the key takeaway from this is that you can define very simple local rules. And when you do that, you can get very complex, sophisticated behavior out the other end. And what this tells us about complex systems is that we should never think of them as a top-down where we break them into their parts the way we've been trained to. What we should go and look for in these systems is how do the components or the agents interact with one another? And that's fundamentally the difference between a simple system and a complex system. If you want to understand a simple system, just break it down into its components, because the behavior will be the sum of those parts. If it's a complex system, get into it and find the interactions. What drives the behavior between the agents? And if you can understand that, you start to be able to understand the system. What's hard about that is that goes against everything we've been trained to do. It's very, very difficult to sit down and go, right, I'm going to try and understand the interactions here as opposed to just the components.
Yeah, I know that's when you explain it that way. Yeah, it becomes on how different parts or even people interact with each other. Like with the flocklings, giving them those 3 rules, you might get different outcomes. You can't just predict where they're going to go or how the swarm is going to form, because it is kind of unpredictable in terms of that. But I guess, I don't know, organized chaos in terms of the starlings and the flocking.
It is like a really good example. Right, you're in Southern California. Let's say a group of people in Southern California decide to buy more and more beach houses. Well, suddenly the price of beach houses goes up because of those interactions. And then other people see that the price of beach houses are going up, and they say, oh, there's money to be made in investing in beach houses. And they do. And then that pushes the price even higher. And then more people go, oh, there's more money to be made in beach houses. And that pushes it even higher.
Yeah.
So suddenly you get this non-linear behavior pops out of this thing, even though the interactions are still linear. But because we're getting feedback and interactions between all the parties, parties, you start to get this unusual behavior. So that's a really good example of
Mm.
what our head, we rationally think people should be buying these houses based on good rational decisions. But because we've got feedback in our complex system, which is the housing market, you start to get different types of behavior.
Yeah, it's really interesting. Yeah, especially with the housing market, everyone makes predictions, but there is that nonlinear element where if everyone knew it, everyone would be rich.
Yeah, exactly right. Exactly right. And I think that's a key thing, that in complex systems we tend to see, particularly in the social ones, we see humans, and it's the interactions that the humans create within the organizational structures that produces this quite strange behavior.
Yeah, and since you're talking about interactions and tying all this back into the Miami Bridge collapse, is it? Can you go into the interactions maybe between? I'm guessing all the parties involved. Did that have anything to do with the Miami Bridge collapse? Maybe with different parties, and maybe that's one of the reasons that led to that failure.
Yeah, so this was a real light bulb moment for me when you look at these failures and you start to say to yourself, well, you've got all these parties, in this case, designers, contractors, and all of that. And if you try and explain the behavior of those parties purely by looking at those parties themselves, and we've talked about, the designer designed the bridge, made some significant design errors. The peer reviewer who was meant to catch those errors didn't catch those errors. Okay, so that's factual. We even know why they didn't identify those errors, because they didn't check the connections and they didn't check all stages of construction, even though they were meant to do so. The Florida Department of Transport required this peer review be undertaken, and it was quite clear on all the things you have to do in a peer review to demonstrate the bridge is going to be okay. Yet, despite that, the peer reviewer didn't do that. And that's very hard to get your head around until you start to take a complexity and approach and say, well, okay, they didn't do it. What was the interactions? And the interactions when it came to the peer review were fascinating. So if we step back to a couple of years before the bridge was being constructed, you have a situation where contractor MCM win the design and construct job to deliver the bridge. They hire an engineering company, designers called FIG, to deliver it. FIG have to engage the peer reviewers. They decide at this tendering stage that they're going to do the peer review themselves. Now, even though the Florida Department of Transport rules says you cannot do this, it has to be an independent third party who does the peer review. Now, FIG did decide that one of their different offices with different people would do the review. But you can imagine they made that decision. They priced up the job with MCM. They won it. We move on. And as we move on, suddenly at a certain point, Florida Department of Transport discover that the peer reviewer is going to be the same company as the designer. And they say, no, you're not going to do that. So now FIG, the designer, have to go out and get quotes to do this peer review. And you can imagine the situation they're in. They've priced up the job, assuming they're going to do it themselves, but now they have to go and find someone else. Along comes the reviewer, a company by the name Louis Berger, and they put in a price of $110,000 to do this peer review. They seem to have got nervous then that maybe their price was a bit high. So they, at some point, go back to FIG and they say, look, we've put in quite a comprehensive check there. We're going to build independent models and check the bridge. So make sure you give us a chance to do a best and final offer on the job. Don't quite know what happened next, but we do know that FIG had 3 bids for it. There are 3 quotes. Louis Berger were $110,000, another group were $85,000, and another group were $63,000. So suddenly Louis Berger are the most expensive by a long shot. As I say, we don't quite know what happened, but we do know that Louis Berger got the job. Their original price was $110,000.
Yeah.
They quote $61,000, $2,000 cheaper than the lowest price. And
they somehow got all the way down and got the job. Interesting.
They got the job. And they had a time of 10 weeks to deliver the job. That got slashed to 7 weeks. So key here is you've got a company Louis Berger, about to do a peer review. The scope of that peer review is actually set by the Florida Department of Transport. You will go and check a bridge like this. So that's non-negotiable. But apparently the fee has been highly negotiable, from 110,000 down to 61,000. And we've gone from 10 weeks to do it to 7 weeks to do it. So you can imagine, if you're Louis Berger, how that drove your decision making. And what we know is that even though they were meant to check all stages of construction of the bridge, and this bridge goes through many different stages, they only checked the final design. And the bridge never made it that far. So they never checked whether the design was okay for the stages leading up to that final design. And the bridge collapsed in one of them. But probably more importantly, this key joint, the one that failed, the one that had been very under-designed and the one that had cracked really badly, they never checked that joint at all. They only checked the members in the bridge to make sure they were okay. Now, I find that really interesting because from structural engineering failure perspective, it's always connections. Connections are the thing that collapse structures. It's very rarely the main members. It's nearly always the connections. So now you're not checking the one thing that really matters. And I think the lesson here is that we expect them to do the scope in a certain way, and they don't. And when we pull back and we look at the interactions, it starts to become really clear why they didn't. And even their engineers, when they were interviewed after the failure by the NTSB, Louis Berger's engineers, they said, we didn't have that type of money available to do a thorough check. So even though the scope stayed the same, the money changed and it led to different behavior. Now, I want to be really clear here. I'm not excusing Louis Berger's behavior. They had a job to do to a certain standard, and that didn't happen. But what I am saying is that if we want to understand why they did that, then it looks like it was time and cost pressure that was a result of the interactions between the parties. So that means if we want to stop this sort of thing happening again, it's not quite enough to say, please do your job properly. You have to say, are we setting up our jobs properly? So that the agents in these complex systems, these construction projects, are actually able to do their job properly. And we discover that that doesn't always happen. And if we pull out a little bit, there's a wonderful piece of research that was done, let me just get the date here, 2014 by Terwell from the Netherlands. And in the Netherlands, around the 2010s, they had quite a lot of structural failures. And they went in and did quite a lot of work to understand, well, why are we getting these structural failures? What's really interesting was they came up with this success factors. In other words, if you have these factors, you have a better chance of avoiding structural failure. And it's interesting when I talk to engineers and I say, what do you think they were? What do you think the most important thing is to avoid structural failure? Most engineers will say, technical competency. That's, if I'm technically competent, I won't get a structural failure. What we find is that's not the case. We find that the two most important things are communication and collaboration. So if you've got a big project with lots of parties, the success or your likelihood of avoiding a structural failure is largely going to come down to the communication and collaboration opportunities there is between the parties. That makes complete sense from a complexity perspective. It's the interactions that matter. But if we go to a really practical sense, it does too, because what it means is if you've got good collaboration, you've got good communication, you'll catch the mistakes. You'll catch the mistakes before they actually eventuate. Because it's the interactions where things go wrong. And there's some wonderful writing about this stuff where they say, we used to have the one engineer on site whose job it was to keep the whole structure inside their head and understand how it worked. But now we've moved where we've got lots of professionals in that process and lots of individual silos and lots of interfaces and interactions between those silos. So suddenly the success of the project is going to depend on how well have we set up those interactions, and how well does information flow? Because that's ultimately what really stops failure in structural engineering and in pretty much every other profession that involves human beings and organizations.
Yeah, that's really interesting. Like you said, yeah, I think for most engineers, yeah, if you know technically what you're doing, we should be good. But as for me, working as a structural engineer and working on these building projects, which are all complex in their own way, yes, that interaction with different, even your team members, but also outside parties, the contractor, architects, like you said, those details are where things fail, and you need to look a little further, a little more thorough to investigate those details and communicating them with the entire design team. And yeah, I think that's, and even when you said about the collaboration between those parties, what those engineers, I guess the pressure that they were in, I mean, it makes sense from that perspective in terms of maybe, yeah, like that big negotiation factor that you said. You can sure that there was probably going to be maybe cutting some corners somewhere to get it half the price essentially. And yeah, cutting the time limit in half too, or shaving off the deadline. That could definitely just, yeah, let's check it. Let's get it out the door. We don't have time. We don't have money. And when you put it that way, it's okay. The technical competence was there, but it just the coordination between both of those parties, maybe it wasn't there because because of all the psychological or the pressure from outside events that had nothing to do with the engineering part. It was kind of just like the pressure that they were in. But yeah, like you said, yeah.
That's right. And I think the key is to say it's not whether or not, if we're trying to manage risk in these big projects, it's not whether or not people should do their job and they should go and do this and it says in the contract they should. It's not about thinking about the project like that. It's about standing back and saying, this project is a complex system. The interactions are going to matter, regardless of what people should do. Given the pressures and the interactions we're going to build into the system, what do we think they're going to do? Are they actually going to go off in these quite sometimes predictable directions because of the way we've set the job up? So I think that's the key in terms of that big picture risk management is accepting that, yeah, it should work like this, but it probably won't. And if it won't, what will it look like given how we've set things up?
Yeah, like what if you cut the amount of time to do this job in half the time? What does that do? Well,
Yes.
you can kind of predict it, like, oh, they're probably
Yes.
going to rush it. They're not going to be well rested, and
Yep. Yeah, that's exactly
yeah,
right. And
it's a good
we
way.
know intuitively that's right, isn't it? It's just the
Yeah,
way things are going to go.
yeah, that's really interesting, and that's a great example. Yeah, I haven't thought about the bridge collapse like that, so that's a really cool insight that I haven't thought about. And yeah, thanks for talking about that. I know you, Sean. I know you have multiple podcasts. Could you tell us about your podcast? That's really interesting, then, and how it can help engineers out there.
Yeah, so we've got four of them, and they all sort of do different things, and some are more dormant than others. Probably one of the key one from an engineering perspective is the Brady podcast. So in that we talk about the sort of stuff we've talked about today. We talk about famous engineering failures and what caused them, with a very big focus on the organizational causes. So dig behind the technical and find the organizational that resulted in them. So if you're an engineer and you're interested in failures, that's definitely the one to go to. A spin-off from that is a podcast series, separate show called Saving Apollo 13. And that really is all about the Apollo 13 mission and, obviously, again, the failure and how people worked out how to do the rescue. We have one called Rethinking Safety. We actually apply a lot of this sort of thinking in the safety space because it's quite interesting. The prevention of engineering failure is very similar in many ways to the prevention of fatalities in high hazard industries like mining and oil and gas. So that's a little limited series called Rethinking Safety. And it's about these principles being applied in the health and safety space. And then the current one that's out is one called Simplifying Complexity. So we don't really have an engineering spin on this one. This one really is designed that if you have an interest in complexity science and you have an interest in exploring it, it's really designed as a nice, easy intro to complexity. So every fortnight we interview complexity scientists from around the world. A lot of them are in the US at the moment. And we take an aspect of complexity, and we usually take an example with that and we discuss it. So examples of some of the stuff we've talked about is we talk about tipping points. Complex systems tend to tip from one type of behavior into another quite suddenly. Think of booms and busts in the economy. Why does that happen? How does that happen? We talk about ants and bees and what they can tell us in terms of how complex social systems work, and it's quite extraordinary how you can take the lessons from bees and ant colonies and apply them to things that we humans do. Because at the end of the day, it's a system of agents with interacting parts. We talk about the economy, and we're now talking about scaling and how when you change the size of complex systems to do really interesting things. So that one's called Simplifying Complexity, and they're all available in the usual places.
Awesome. Yeah, we'll make sure to link those below. And for our audience members, make sure to go check those out. Sean, as my final question is, do you have any final career advice for structural engineers that maybe want to get into this type of forensic science?
Yes. So there's a couple of thoughts on that. If you're interested in forensics, there are fabulous books out there on forensic engineering. There's a wonderful one called Beyond Failure by Norbert Delat, and that'll give you a real insight into how structures fail. The key thing is, if you want to do forensics, you have to get around real structures. So you can't do it from the design office. Design and forensics are very, very different things. So get out there, do work that allows you to assess older structures that are non-code compliant and work out what they're actually doing and how they're actually behaving. So go and get that sort of expertise under your belt. Don't just sit in a design office that's pushing out new designs. You need to go a little bit broader than that. And the other piece of advice I would give anyone really in the profession is that I think we engineers, not just structural engineers, but many of us as engineers, we feel like we have a set of unique problems that we're always trying to solve. And we tend to feel that it's our job as the engineers who are dealing with them to solve these problems. The advice I would say is that because we're organizations, because we're humans, a lot of these problems are being tackled outside of engineering. There's so much engineering can learn from medicine and how they produce better, safer outcomes. The same from business, the same from health and safety. So I would say look outside the boundaries of our discipline for the solutions of some of your bigger problems, because we're all the same and our organizations are all the same. There are plenty of people around the world working on them.
Yeah, many problems are translatable to different industries, and end of the day, we're all human, and I'm sure there's like you were saying, learn from different types of industries, because that problem is probably someone's tackled it or trying to tackle it. So yeah, great advice. And Sean, I just wanted to end it off here and thank you so much for coming on and talking about complexity science. That was a really interesting topic, and we'll make sure to go check out that podcast. And yeah, thanks again.
Thank you very much, Matthew. It's been a pleasure.
I hope you enjoyed the episode today. We'd love to hear your feedback, comments, and/or questions. To leave them, please visit structuralengineeringchannel.com. There you'll find a summary of the key points discussed in today's episode, which is episode number 100, as well as links to any of the resources or websites mentioned during this episode. Don't forget to subscribe to Apple Podcasts, Spotify, or wherever you listen to your podcasts. Until next time, we wish you the best in all of your structural engineering endeavors.